When we're talking about traveling waves, two very important things to remember. First, every traveling wave is caused by some kind of a disturbance at the source. Commonly, that disturbance is an oscillation. And as we'll see in the next couple of days, we'll be able to relate everything we know about oscillations to wave phenomena. The other important point is that the speed of a wave depends on what kind of medium the wave is traveling through. That some properties of that medium will determine the speed of the wave. For example, as you saw in the reading, a sound wave traveling through air depends on the temperature of the air and what kind of molecules are in that air. And similarly, the speed of a wave on a string depends on just two aspects of the string: the tension to which the string is tightened. Right? This T is going to represent tension, not period of an oscillation, tension. And then this other factor here, which you can sort of think of as a one-dimensional density, mass per length. In a way, it's a way of measuring how thick the string is, how many kilograms per meter or how many grams per centimeter, whatever. But let's just look at a couple examples of how this works. Let's say you've got a string and it's at some tension, call it T1, and as a result of that, the wave speed is 1 meter per second. And let's say now you tighten the string so that now there's a higher tension. Let's say it's 25% tighter than before. The new tension is 1.25 times the old tension. What's the new wave speed? Well, we kept the same string, so same length, same mass, so this factor here in the denominator is the same. The only thing that differs here is tension. So it's helpful to rewrite this equation a little bit. Write it this way. Wave speed is 1 over square root of that mass to length ratio. This is the Greek letter mu, times square root of tension. And now you've got an equation that's in the standard form of direct proportionality, where you've got some variable, speed in this case, equals a constant factor. Right? We did not change the string, so this did not change. This thing here is constant, times some other variable. And remember the point that's kind of tricky, but very, very important. When we say that this is the form of proportionality, what we mean is that everything that isn't lumped into the constant factor becomes the variable x. All there is on the right side is the variable and all the constant stuff. Well, here in this equation, here's the constant stuff, and here's what's left over after factoring out the constant stuff. So this is the variable square root of t, not t itself. So direct proportionality between, that all implies there's a direct proportionality between wave speed and square root of tension. What does that mean? Remember, direct proportionality means when one thing changes by some factor, the other thing changes by exactly the same factor. So if we knew how square root of t changed, we would know that wave speed changes in exactly the same way, changes by the same factor. This equation here tells us how tension changes, but we need to know how square root of tension changes, and we can get that information just by taking the square root of this whole equation. So let's do that. Square root of T2 equals square root of everything on the right-hand side, which is square root of 1.25 times square root of the old tension. So square root of tension changes by this factor, square root of 1.5. Old square root tension equals this number here, square root 1.5, and that old times this factor of square root 1.5 gives you the new square root tension. So wave speed changes by exactly the same factor. New wave speed is that same factor, square root of 1.25 times old wave speed, which was just 1 meter per second. So after you get your calculator to tell you what the square root of 1.25 is, you'll find that the final answer is about 1.1 meters per second. But the tension increased by 25%, but as a result, the wave speed increased by only about 10%. Let's look at another example. Let's say this time we'll exchange one string for a different string. We'll tighten them to the same tension, but we'll have different strings made of different material, and so this factor will be different. Let's say for one particular string with one particular value of mu, let's say again the wave speed is 1 meter per second. Now, imagine replacing that string with a thicker string. Thicker means more massive, which means more mass per centimeter, more mass per millimeter, whatever. So let's say the new mass per length is 1.5 times the old mass per length. In other words, 50% greater. The new string has 50% more mass per unit length. Okay, so now in this case, like I said, we're keeping the tension the same in both strings. So let me rewrite this equation to separate out more clearly the constant stuff from the variable stuff. Speed is square root of tension times 1 over square root of mu. And that's the general form for another kind of proportionality, inverse proportionality. We've got one variable equals constant stuff, which in this case is square root of tension, times or divided by some variable. In this case, the variable x is square root of mu. So in this case, we can say that y and x are inversely proportional. In that case, y corresponds to speed, x corresponds to square root of mu. So speed is inversely proportional to the square root of mu, or proportional to 1 over the square root of mu, however you want to say it. But whenever you have this kind of inverse proportionality, the proportional variables behave a little bit differently than they did in direct proportionality. Here, obviously, if this variable gets bigger, this one gets smaller. If this variable gets smaller, this one gets bigger. So in inverse proportionality, the two variables change the opposite way. If this variable doubles, for instance, becomes 2x instead of x, then you have to do the same thing to both sides of the equation to keep the equation equal. That means that this variable has gone from y to 1/2 y. In other words, this variable doubled, and as a result, the other variable was cut in half. That's the way inverse proportionality always works. When one variable changes by some factor, x changes by a factor of 2 here, the other variable, y, changes by the inverse. The new value here on the left-hand side is y times 1/2. So that's what we've got here. When square root of mu changes by some factor, wave speed will change by the inverse of that factor. So again, we want to see how square root of mu changes. And so we use this equation again, which tells us how mu itself changes, but just take the square root of the whole equation to find out how the square root changes. And it's going to look kind of like our previous example here. Nu square root of mu, square root of this equals square root of all this, so square root of 1.5 times square root of old mu. So old square root mu times this factor gives you nu square root mu. So being inversely proportional to speed, speed will change by the inverse of that factor. Nu speed equals 1 over square root of 1.5 times old speed, which was just 1 meter per second. And when you do the numbers, you will come up with about 0.82 meters per second. Okay, one more example. This one has a little extra complication to it. It's worth something that you knew at one point, but it's good to be reminded of it. Thinking about the speed of a sound wave traveling through a gas, traveling through helium, traveling through normal air, traveling through carbon dioxide, whatever. And the rule goes like this. The speed is equal to some factor that we call gamma, lowercase Greek letter gamma, which basically depends on what kind of molecules you've got in that gas, diatomic, triatomic, whatever, times the R that you also see in the ideal gas law, same R that you saw in the old ideal gas law. Pressure volume equals number of moles times R times temperature. And temperature is a factor. And then the molar mass down here at kilograms per mole. Now the important thing to remember here is that in all those thermodynamic and ideal gas equations and stuff like that, temperature is always, whenever you plug in a temperature number, it must always be in Kelvin, not Celsius and certainly not Fahrenheit. So let's say at normal room temperature, 20 Celsius or 293 Kelvin, speed of sound in air is 343 meters per second. Now let's say it's a warmer day. 20 Celsius corresponds to 68 Fahrenheit. Let's think about 30 Celsius, which corresponds to 86 degrees Fahrenheit. That would be equal to 303 Kelvin. And in that case, what's the new wave speed for the sound waves? Same deal. We can think about this a little bit more clearly if we lump together all the constant factors. The only thing that's changed here is temperature. So what we really have is wave speed equals square root of gamma R, the so-called ideal gas constant, over molar mass times square root of temperature. And again, there's a direct proportionality. Some variable, speed in this case, equals a whole bunch of constant factors, square root of gamma R over mass, times another variable, square root of temperature in this case. So our proportionality that will help us is wave speed is directly proportional to square root of temperature, as long as it's always the same type of gas. Same type of gas ensures that that factor and that factor will always stay the same. So we want to know how square root of temperature changes. And then remember that temperature means Kelvin temperature. So the new temperature was 303 Kelvin. The old temperature was 293 Kelvin. So new temperature is just 303 over 293 times the old temperature. The old temperature itself was 293. So divide by 293, multiply by 303, that gives us 303 for the new temperature. So here's the factor by which temperature changes. We want to know the factor by which square root of temperature changes, so just take the square root of the whole equation. And there we have it. Old square root temperature times some factor gives you new square root temperature. So anything that is proportional to square root temperature changes by exactly the same factor, changes by this factor. And it's a speed of a sound wave that is proportional to square root of temperature. And so if square root of temperature changes by this factor, then the speed of the sound wave changes by that same factor. So what have we got? New speed equals that factor, 303 Kelvin over 293 Kelvin times old speed. This was 343 meters per second. So the new speed comes out to, just rounding it off to 3 digits, 349 meters per second. Okay, and then you can try some of this at home.